All right, good morning, everybody. Today we are continuing through our discussion of mechanics of materials. Today is lecture 10, and today we will begin chapter 2. So chapter 2 is a topic called stress and strain under axial loading. So we'll define some terms and we'll expand our discussion from chapter 1. So we're going to come over to the document cam and take a look at the first thing that I want to do is to talk about the difference between stress, which we discussed in chapter 1, and strain, which we will discuss in chapter 2. I want to explicitly state this, that stress and strain are not the same thing. They are not equal to each other. In everyday life, when we talk about stress, you've already learned, of course, that stress in terms of engineering content is not the same as stress in terms of being a human being and having to cope with things and so forth. But when we talk about stress, we talk about sigma, which is normal stress, and tau, which is shearing stress, and they both have dimensions. Square brackets like this indicate that we're talking about dimensions. Both of them have the dimensions of pressure, which is a force over a length squared term. And the difference between them is the geometry. This has to do with either tension or compression, and we've said that we don't have a sign convention yet for tau, but it is to follow. So we haven't defined this rigorously yet because tau, or shearing stress, there is a difference between positive and negative, but it's not a physical difference in property like the difference between tension and compression. Now, strain, on the other hand, refers to a deformation that may be caused, not necessarily, but may be caused by a stress. And the deformation in the case of normal stress is referred to as normal strain, and it is designated by the Greek letter epsilon. So I have it drawn as just a small curved E. And when later we talk about the strain caused by a shearing stress, it is something referred to as shearing strain. And it is designated by the Greek letter gamma. Right? Now today we're going to talk about epsilon. We're going to talk about normal strain. Epsilon is a dimensionless change in length that may be due, you'll find out later it can be due to other things as well, but may be due to a normal stress. So essentially, if sigma is positive, that means that we are in tension, and in general, epsilon will also be positive. In other words, there will be an elongation. And if sigma is negative, that signifies compression, and that would be a negative epsilon, which is a shortening. Okay? Now, if we have a structural element, I've drawn my ceiling crooked here, hope you'll forgive me. We have a structural member that is welded to the ceiling, and we pull on that structural member. We know by now that we will have some sort of a sigma in the amount of P over A. But if this structural member started out as being some length L, when we add the load to it, it will now be some new L. In other words, it will elongate. And we could refer to this as L prime, and we can refer to the difference in the length by the Greek letter del. So del is the difference in length here caused by P or sigma. In other words, caused by the load or by the normal stress. And so we could say that if del is the difference, we refer to that as just the amount of elongation. And we can then say epsilon is equal to del over L. In other words, epsilon is equal to the change in length over the original length. So in other words, it's a fraction that the structural member has elongated, or in the case of compression, been squished upward. Now, in statics and in physics, we have always sort of implicitly assumed, good morning, we've always sort of implicitly assumed that the structural member that we subject a load to is capable of bearing that load. But in real life, structural members deform or break in response to load and stress, among other things. So how a structural member, this is what we're going to talk about today, deforms is a physical characteristic of that material. Of the structural member. And when I say that, both the material and the geometry being the size and the shape. Okay? So the first way that we classify a material is that it is either brittle or, this is a spectrum, it's not an either or sort of a thing, that it is ductile. And what brittle refers to is if sigma ultimate is exceeded, the material breaks. And for ductile, if sigma, I don't know if I want to call it ultimate, so I'm going to put it in quotes, we're going to talk about that, is exceeded, the material, let's even say the structural member, to be more, the structural member doesn't break at first, but it yields in some manner. So, if we were to take a completely brittle material, and so this is one end of the spectrum, and if we were to plot sigma, normal stress, versus epsilon normal strain, what we would see is that when we have no sigma, we would have no epsilon. In other words, no normal stress, no normal strain, no load, no change in length. And then as we add some sort of a load, we would also see that the material would get a little bit longer and a little bit longer until it would suddenly rupture. So we could call that sigma rupture or ultimate. Right? Now, this would be a perfectly brittle material. Let me get this. I'll put this so we can take a look at this. Probably look at some other stuff. Okay. So if a material, there's really no way to draw something that is perfectly ductile, but let's just say a very ductile material. If we were to plot sigma versus epsilon, we would see that at 0 sigma, we have 0 epsilon. But when we reach something, I'm going to refer to it as sigma yield, where the material begins to change due to the load, that something will happen, that it will continue to elongate, that it will bear stress in some different way until at some point it ruptures. Now, the curve could look like this, or for other materials, it could look, we'd have the same sigma yield and the same profile prior to yield, but maybe it's going to look like this and rupture like this, or maybe it's going to, I need a different color marker here, yield and then continue straight on this line for some distance until it ruptures. So ductile materials all behave in a specific way. Each material is a little different.
So what would be considered like a brittle state?
A brittle material is like concrete. If you pull on it, it just breaks. Wood is somewhat brittle. Diamonds are incredibly brittle, yes. Then ductile materials, metals in general, one of the key properties of a metal is that ductility, that ability to yield rather than rupture.
So would that be almost its atomic structure? That would be
It is. Yes, it is. And what actually happens, I'll bring something next time. I should have brought it today. Maybe I'll go get it. We'll see what happens. But if you take, for example, a wire, and if you, well, let's see, maybe if I have a paper clip here. Let's see what has been left to me to play with today. Maybe nothing.
Now, is brittle and ductile completely on actual length tension?
No, this is one of the simplest descriptions. Brittle ductility is a multifaceted property. Okay, but let's think. Maybe we can do a thought experiment. If you had a paper clip, and if you bent it a bunch of different times, have you ever done this, where you take something and you bend it or you stretch it a whole bunch? What happens? What is the difference in the feel of the paper clip itself? Has anyone ever noticed this? Well, yes. It becomes warm. That is exactly correct. What that is a release of energy. And you're actually changing the structure on a molecular level of the metal in that paper clip. So that warmth is a release of energy. It's an exothermic process. Very, very good. I usually have them and give them to you. I should have done that today. But that's exactly what happens. So go home, there's your homework for tonight. Go home and get a paper clip or something similar and bend it back and forth a number of times and feel that the temperature changes. That's a release in energy. So what happens with a ductile material is that after we reach this point of yield, whatever it looks like, we refer to that point, we also refer to it in a brittle material, as the elastic limit. And very often, with brittle materials, obviously, we never design past the elastic limit. With ductile materials, you will sometimes design past the elastic limit, but the properties of the material, and therefore what you can depend on that material to do for you, changes significantly after you reach the elastic limit. So this is why, like, a big time where this happens is with horse trailers, for example. Horse trailers are loaded in a very dynamic and strange way, but when you have a whole bunch of horses and you're pulling a trailer over the road and it's getting bounced around a whole bunch of different ways, at some point the structural integrity of the horse trailer will actually become different, and you can't load it the same way as you could when it was new. Okay? So what you've done is you've actually, even though you've loaded it and gotten away with it, you've done something and changed the structural integrity of the material that the horse trailer is built from, and you can no longer depend on it to behave the same way as it did before that happened. So as engineers, at least at this stage of the game, when we're in mechanics of materials, so let's say, I'll say for sure in ES 2410, we always design below the elastic limit of a material, of a structural member. Okay? This is where you know how your material is going to behave, whatever it is. Okay? So generally speaking, we want to make sure that we stay below that. Now, there's a picture in your textbook, and this is on the top of page 60, that discusses the behavior of a particular sort of ductile material. And then there is another picture. Well, we'll just go through some of these graphs. But let's talk about some of the regions that can occur. These don't necessarily all occur, and they occur in different amounts, which is why we're talking about here a low carbon steel. And then we compare it to an aluminum alloy. But I'm going to draw this one so you can see what it looks like. But we start at 0, 0, where we have sigma versus epsilon, and we stay within the elastic limit to some particular value of sigma, which once again we refer to that as sigma yield, or sigma sub y. And then the material actually yields. And what happens is you see a dip in sigma for epsilon. So since this is the change in length, and this is the change in stress, what we're really talking about is you pull on something with a particular force, right? And then you pull on it with less force and it continues to elongate. Now, you can see that with other things like silly putty. If you have silly putty, if you have like a little sausage of silly putty and you pull on it, it'll get thin, right? And then it will start to sort of float, you know? So you see that you can pull on it less hard and it will still continue to elongate. And actually the rate of elongation will increase. Then what will happen is it'll sort of like change its mind, and it will require more stress to continue elongating. So this section is referred to as yield, and where it needs more stress to continue elongating is referred to as strain hardening, because it feels like it hardens a little bit at that point due to either the stress or the strain. And at some point you will reach sigma ultimate, which can be above sigma yield. And that's the point where it will not take any more stress at all. And then you'll see this area this curve start to decrease, and then it will finally rupture or break at this point. And the difference between here and here, this is where you'll see that actual, if you continue to pull on a section that looked like this, it will actually sort of develop a little neck. And so it gets actually narrower. And so this region is referred to as necking. Now, the one thing I want to point out is because sigma is a force over an area, in the region of necking, that area actually gets smaller, doesn't it? So sigma would actually increase. So in other words, you're decreasing the force quite a lot in the region of necking. When this starts to happen, failure is imminent. No matter how ductile the material is, the failure of that material is imminent, and you need to quit doing whatever you're attempting to do is going to result in something that's not going to bear a stress anymore.
So with your low carbon steels, this is identical from its stress to compression?
Not really. It depends on if you exceed the limits or not. If you stay within the limits, it does. It will be identical. So in other words, if you design within the elastic limit, which is from 0 to sigma yield, tension and compression will behave exactly the same way for all referred to as homogeneous materials. There are some heterogeneous materials that don't act that way at all. One is concrete. Cast poured concrete behaves extraordinarily well in compression, very, very poorly in tension. And so but because concrete is everywhere, the word is a vocabulary word for the day. Concrete is ubiquitous. Ubiquitous means everywhere. Just like we can say water is everywhere. When we study fluids, why do we study water so much? Because water is ubiquitous. We use it. It's everywhere. It has some strange properties, but because it is such a commonly used fluid, we study it very, very carefully. The same with certain kinds of refrigerants. But anyway, that's another story. But concrete is ubiquitous, so we study it quite a bit. Now, if you look at this is actually going to answer Dane's question. And the picture's a little bit better than I'm able to draw. So I'll go through this with you. Basically what we have here is a mild steel that we load it and then we reverse load it. And reverse load it means we put it back into compression after we've exceeded the elastic limit. So in other words, we start here at 0, 0. Okay. Now if you don't start at 0, 0, if epsilon at 0 or sigma at 0 is not equal to epsilon at 0, you have a material that requires some threshold of stress before it starts to deform. That is referred to as a Bingham plastic. There are all sorts of different materials, but we're talking about normally behaved materials where as soon as you start to pull on it, it starts to change its shape or its length. Okay, so mild steel, all the steels are that way. So here we go. We talked about this part where we increase the load. We're still in the elastic limit, and so epsilon increases. Then we yield. It dips down a little bit where we have that yield, and then we get into the strain hardening region. Now what this indicates is before we get to rupture, we start to decrease our load. All right? So what does this difference indicate from here to here? Well, that means that after we've yielded that material, even if we take the load back to 0, it doesn't go back to its original size and shape. That's sort of the hallmark of having exceeded the yield strength of a material. So what we do is we depress it. We actually here would put it into compression, and then we remove the load again, and guess what? We're at 0 load, and now we have an intermediate length between the two. So then we increase our load a little bit, and the material has become deformed or has become structurally altered in that way of the hot paper clip, and it will break at a value below sigma yield. Okay, so that's what this curve over here indicates. This curve indicates that we get into the yield range. We don't get into the strain hardening range. We just get to the yield range. We remove the load, and once again, we have an increase in length because we have allowed the material to yield. But then we take the load back to a negative, and we continue. We have sort of this strange behavior where the material continues to shrink without really removing very much of the load. We just remove it a little tiny bit, and then we remove the load completely, and we have a shortened material because of this cycle of loading. And then if we increase the load, once again, we have a rupture at a value below sigma yield.
So if we pull it past its yield and
yes.
press it again, it becomes brittle?
That's mild steel does. That's right, and most materials do. The real message for these graphs, they're all different. Every material behaves differently after after you exceed yield. The real message I always tell my students is like, don't let this happen to you. There are very specific cases where you, when you are a very sophisticated engineer, may be called upon to design beyond the yield, but you will know so much about that particular situation that you will have all of your variables accounted for. In general, this is like those old maps of the world, if you've ever seen, where map makers, prior to understanding that the world was round, or maybe the church was saying that you couldn't believe that the world was round, they would sort of draw these really good maps in the center of a piece of paper, and around the outside it would say, if you go here, there'd be dragons. Well, there weren't really any dragons. Nobody was really going to fall off the end of the world. But really here, this is the place where we want to design as students in mechanics and materials, and also as engineers dealing with a variety of materials in a variety of situations. If you go beyond here, there'd be dragons, and you need to be able to define your dragons very well before you do that. So, and it would be very specific to what you're designing for, specific to what you're designing with, specific to the needs of that particular project. So, and definitely the dragons are beyond the scope of this course. So it's very interesting to me to talk to, but the main message in terms of our math for ES 2410 is stay within the elastic limit of the material, regardless of whether it's ductile or brittle. Sound like a plan? All right. So you think, well, there's all this exciting stuff going on beyond the elastic limit, so is this the only thing that we're interested in? And the answer is, for this class, yes. Okay? We don't want to go beyond the elastic limit. So let's draw another graph showing just the elastic limit and talk a little bit about this. Below the elastic limit, let me do one other thing here. We use the word elastic limit to indicate this. And if you think about it, it's like a rubber band that is not deformed, or you haven't left it in the windowsill and gotten sun checked or whatever. But when you stretch it, it goes back. Stretch it, goes back, right? Elastic. Elastic band, elastic limit. So we're talking about materials that are still behaving in that way. We're not talking about Bingham plastics. We're talking about materials that when they have 0 sigma, they have 0 epsilon, and then they begin to move up in a homogeneous fashion until they reach sigma yield. So within the elastic limit, this is a straight line for most materials going through 0, and the slope of this line is referred to as E, capital E, which is called Young's modulus, or the modulus of elasticity. Okay, so if you look at this graph, if it's a straight line, we know that the slope of a straight line is equal to the change in y over the change in x. The change in y here is sigma minus 0, and the change in x is epsilon minus 0. So we've defined two things. First of all, that it's a straight line. Second of all, that it goes through the point 0, 0. So in this case, m, which is equal to E, is equal to sigma over epsilon. And this is called Hooke's law. And Hooke's law is a very useful computational tool for materials behaving within the elastic limit. So we're going to expend our conversation about this at least on Wednesday and maybe a little bit on Friday. But there are a couple of things about Hooke's law. Hooke's law only works in the elastic limit, and it only works for normally behaving materials. It also tells you nothing about the strength of the material. It tells you how stretchy the material is. Okay? So the smaller epsilon, or excuse me, E is, the smaller that the modulus of elasticity is, the stretchier the material is. In other words, if the slope were like this, that would mean, wow, I don't need to put very much sigma on it in order to get it to stretch quite a bit. And since epsilon is in the denominator, a larger denominator means that the value is smaller. So large E means very stretchy, and small e means not so stretchy. And stretchy is not a technical term. That's just a descriptor.
So the angle of E defines how elastic.
Exactly. The value of E defines how elastic it is, and that's based on, that is written out in Hooke's law. Now the other thing is, materials can have the same value of E, and yet one can be much stronger or weaker than the other. So if we have sigma epsilon goes through 0, we have one material that looks like this and yields. We have another material that looks like this and yields. And we have yet another material, which I don't have a marker for because I've lost my black one, that does some really big thing like this and then ruptures. All three of these have the same modulus of elasticity, but significantly different amounts of stress they will take, or strengths, as measured by either sigma yield or sigma rupture, right? We could also have another material that just goes like this and then just breaks. That would be a purely ductile material, or purely brittle material. All right? So E tells you what it tells you. And when can you use Hooke's law? Hooke's law is only applicable in the elastic region. So before sigma yield or sigma rupture, whatever that value is. So before you decide if you can use Hooke's law, you have to assure that you are in the elastic region, that the material is still behaving in an elastic manner. So you also need to know where sigma yield or sigma rupture is before you can use it. All right, do you guys have any questions at this point? Well, let's call it quits for today. And so I will turn off lecture 10. We'll come back and do lecture 11 on Wednesday. And also on Wednesday, your homework is due. So if you have any questions, let me know really quickly at the beginning of class before we continue with our discussion of chapter 2.